Okay, so thank you so much for inviting me. So I took a very short trip from Long Island to here. So I'll be telling you about some work about line defects that I've been doing with several people in Stony Brook and also at Weizmann. So it's based essentially, it's a collection essentially from these three works and this work in progress with Zorko Mikotsky, Mark Mezei, Avi Moshe, and Ofer Aroni. So yeah, don't worry, I don't want to talk about all this in those papers, but I'll try to give you some overview. So what am I going to talk about? I'm going to talk about, as the title says, about line defects. So line defects are probes of a system which are extended in one dimension. Typically we think of the dimension as time, but you can also think in Euclidean, it could be extended in Euclidean space. So in two-dimensional system, line defects arise as interfaces and boundaries. Famously, the Kondo problem, which just describes some impurity interfacing between two sides of a material, led Wilson to the development of the normalization group. Before all the stat method we studied, Wilson was motivated by the Kondo problem in 2D. And then it also led to many developments in integrability. In three-dimensional symmetry defects and spin impurities are typical examples. In particular, spin impurity is what happens if you replace one atom of a material layer with a doping atom, and it's extended in time, so it's a line defect. And finally, in four dimension, we know about Wilson tube lines, which are just the effect of a heavy charged particle in your gauge theory. And it's typically interesting to study the fate, to detect the phase of the theory, the study of Wilson tube lines. So the common theme of today will be studying examples that are very well suitable to be studied within a framework of renormalization group, or a somewhat NRG approach on line defects. I'll explain what this means in a while. So to define more sharply a problem, I will need to give you some rather formal introduction about RG flows on line defects. So I think it's useful before doing that to explain the physical problems I want to address from a more mundane viewpoint. So the first part of the talk will be about 2 + 1 dimensional materials, so mostly at criticality. So I'll consider it can be a magnet at the transition point. And I'll consider two experimentally relevant examples of this. So you can think of your magnet as the material made of spin in each one in a lattice size. It's like a realization of the Ising model. The first defect you can study is what happens if you turn on an external field localized on a single lattice size, or on a bunch, of course. In long distance limit, it doesn't matter if it's one or a few. This is a defect because it's extended in time, and so again, it's localized in space, and it's relevant in Monte Carlo. So there are some critical exponents associated to this defect problem, and I will try to extract them. The second problem I'll study is more common, in fact it's even more studied, is the one of impurities. Here again, what we will do, we will replace one of the constituents of the lattice with a different one, which you can think as a different atom, which has a different spin. Typically, the universally class is labeled by the spin of the atoms of the material. So here we'll put a spin in a different representation, and this will lead again to some problem that I can study within RG. If you want to take home message of the first part of the talk, will be that these two apparently related problems, so these two apparently related defects, are actually the same in the limit in which the spin of the impurity becomes large. So the critical exponent associated with these two problems become the same when this S-imp becomes very large. Physically, it's because you can think of an impurity as becoming a huge source when the spin is large for the bulk material. I'll explain that in more detail. Please interrupt me anytime for questions. So the second part of the talk will be about a work in progress, which is about Wilson lines. So I'll take some four-dimensional gauge theory, and I'll take it conformal or quasi-conformal. Massless scalar QD would be enough for me, so nothing too complicated. And I'll consider the theory represents a Wilson line. If you don't like thinking of an abstract object, you can think of a heavy external nucleus traveling in your theory with a charge Q. And the question I'll ask is, with which amount of charge am I allowed to probe the theory? So why is this not a trivial question? So a Wilson line sources a large Coulomb potential, as we know. So a nucleus has a large Coulomb potential. But in the momentary matter, a large Coulomb potential is a large electric field that we were instructed from Schwinger 50 years ago, or maybe 70, I think, that leads to an instability for the matter. So the question here will be, what are the consequences of this Wilson instability for the theory in the presence of a Wilson line?
But you're in 3+1 or in 2+1?
3+1. 3+1. No,
2, but 1 over R, it is, I thought that it in 3+1.
3+1 then. What dimension? 3+1.
3+1. Yeah, no,
Yeah, so the formula is that. So the formula is like, so I'll discuss
Yeah, so
first materials in 2+1 and then this theory is 3+1.
got it. Yeah.
Sorry, you're right. I should have specified that. Thank you. Yeah, and actually there are, you can also take layer of materials immersed in a, like a 2D material in the 3D space with electron. So this is like graphene. The Coulomb potential is in the full space, but the graphene is a layer. And you actually have similar phenomena. I won't discuss it, but it should be apparent that I think we generalize that. So what you're allowed to expect is that somehow matter will pop out around the lines, around the nucleus at traveling time, and we'll kind of screen it. So if you want just a slogan, the result will be that besides some of the old Wilson lines we know, some Wilson lines with sufficiently large charge will become unstable and get screened. And perhaps more surprisingly at this stage, besides there are also new Wilson lines. So it's not enough to specify the charge of a nucleus to decide what is its physics. We have to specify an extra component, and this will lead to existence of two conformal lines in formal language.
Local operator analog of this? I think that also for local operator there will be something which triggers. But I'm not familiar.
So local operator. So you're saying if we put local operator, can you write a local operator, a gauge invariant local operator with large gauge charge? I don't.
Well, but I can think it more generically. One can think of some local operator which triggers instability by being coupled.
Right, but I mean the instability is because this guy has some sources some Coulomb potential. To establish source of Coulomb potential, you not to do it with a local operator.
No, maybe it will be different mechanisms, but I can ask him more generously.
Yeah, no, I'm just saying that I don't know, and the reason why I don't think it's obvious is because I don't know how to create such a Coulomb potential with a local operator.
But in terms of notation, T here it is a real time, or it's just parameter along this?
In this problem, I think T of time all the time. In this problem here, I think T of time all the time.
Just real time.
Real time, yeah.
Yeah, but so it's not like geographically some kind of a loop in space.
No, I'll take a line traveling straight in time. I mean,
I see. So it's just like a fixed charge and okay.
Yeah. I mean, this instability, as we see, is triggered really by physics close to the line. So even if because that's where the gauge potential is large. So really it doesn't matter too much, but I will discuss the simple case of the line traveling.
But if I think about Euclidean theory,
there will still be instability, but the electric field is imaginary. Euclidean signature.
And then in the Euclidean series, there is no other restriction. Nothing special happens at latch key.
No. The Euclidean theory, the electric field sourced by the line, is imaginary. It doesn't lie like us. So the same physics. I mean, the fact that this instability means that the Euclidean theory is not reflection positive. It insists within the line.
So you're not rotating A0.
I mean, you rotate. I mean, I'm saying if you rotate A0 and T both, which is what you're instructed to do by the weak rotation, then the electric field becomes imaginary. That's what's in the typical finger effect. It seems to have a BE symmetry, but the physical thing is B to IE with an I.
But your Q is Q square effectively or what? Because you have Q in definition and also you have Q in A0.
I'm taking Q positive for the sake of it. You can take Q negative. You should take Q square, of course.
So it's Q square.
It's Q square, yeah. You're right. Yeah, I was a bit slow. But in this part of the talk, I will be for simplicity of form and think of Q positive. You can take charge conversion invariant. Okay, so this is what I want to talk about. The rest of the talk will be organized as follows. I'll have first, as I said, a formal introduction, the viewpoint I'll take on these problems, and then I'll discuss these two problems in order, and finally I'll have a summary and outlook if time allows. Okay, so what is the viewpoint I want to take? I'll start very generally. So how do we think? Let me first remind you of a formal or condensed matter way to think of quantum field theory. So a quantum field theory is typically traced by some, we say one length scale L, could be a mass, a scattering length, whatever we can. And then we can look at the system either at distances much shorter than length scale L or at distances much larger. And of course, at this distance, we are insensitive to this scale L, so the theory will exercise some kind of scale invariance. So it will be a CFT, such a conformal field theory, or it's well approximated by the conformal. What connects the UV scale invariant description, the AR scale invariant description, is just the energy flow. So But what I'm saying is that we can think of a quantum field theory formally as energy flow between a CFT in the UV and a CFT in the AR. Just as before. So, okay, this is the definition of CFT. If you want, it's a theory invariant of the conformal group, which is this. And an important point is that monotonicity theorems guarantee that the energy flow is irreversible. So the CFT in the UV is different than CFT in IR. You might ask, can you happen to be in the same description of short and far distances? And the answer is no. And it's guaranteed by these theorems, at least as long as you care about physical dimension as before. So it should then be clear that to understand the fate of the RG, it's important to understand the fate of CFTs. So a very brief reminder, CFTs are characterized by their operator spectrum. So by their algebra, but most importantly by their scaling dimension, which just tells you how, which with power correlation length decay. And as I'm sure you all know, the space of operator scaling dimension less than d, the number of space-time dimension, triggers is the space of the RG flows. So given all the relevant operators I have, I can construct a quantum field theory perturbing the CFT with those operators in this way. And the numbers of coupling here are essential to parameterize the RG flow. The typical goal in this kind of discussion is finding the infrared description that correspond to these couplings. So in other words, the typical goal in condensed matter science is finding the IR CFT that describes the endpoint of the flow, which is triggered by these couplings. So typically, a picture you might have all seen, say in such the book, is that depending on some coupling and the temperature, you end up either in some phase, other phase, or a quantum critical phase, something like this. So this is typically what we want to achieve, drawing that diagram and understanding what are the physics in each point of this diagram. This okay for everyone? Okay, so how do we make this viewpoint useful in the study of line defects? To this aim, I need to remind you or explain that there are two equivalent viewpoints on line defects. One of it is thinking of the line defect as an operator. So you insert some non-local functional of your fields in your path integral, your Wilson line, say some function of the gauge field, or you specify some boundary condition or one these offers. Okay, that's fine, but that's not most useful for us. For us, it's more useful to think of a line defect as defining a new theory. So you take your path theory, and you modify it with a term on the action localized on a 1D surface in a semi-classical sense. But of course, you don't need a semi-classical description for this to be true. Physically, it's because, imagine it's a Wilson line, it's traveling in your space, and then if you quantize slicing time in this way, it's clear that each point in time, you have an extra element if you read space, which is the quark traveling of the Wilson line. So that's why it's convenient to think of a new inverse space and therefore of a new theory, which is a defect quantum field theory. And that's the viewpoint I'll take. So defects can be thought either as new theories or as operators. Okay, as I said, I'll study defects, or as I should have said, I'll study defects in CFTs. There's mostly because I'm interested in infrared physics, so and every theory in the infrared is a CFT, so there's no big restriction on that. So once a defect is embedded in a CFT, it may or may not preserve a subset of the conformal group. So we call defect conformal field theories those defects that when placed on straight circular line preserve the one-dimensional conformal group around the line. So this is SL2R, just scale transformation on the line, special conformal and translation. And typically assume also rotations around it, but it's not too important. So notice this doesn't need to be the case because a defect can have some quantum mechanics living on it which interacts with its own scattering lengths or it has its own properties which may not be scale invariant even if the theory is. And therefore, once I embedded with this definition, I can think of a defect quantum field theory in the same way I think of a quantum field theory, as I said before. Namely, I can think of a generic massive defect as an energy flow between a defect CFT in the UV and a defect CFT in the AR.
In this discussion, one already just use a defect really kind of straight line, or
no, it doesn't need to be straight. I mean,
but then there will be no rotation group, let's say. So
you can put it on a circle, but I mean the point is that defect conformal field. So the local properties of the defect do not depend on how you place it. Okay, typically we think of straight line, but whether it actually preserves the full global conformal group, of course, it's going to be on a straight line or a circle. So it's a bit like saying, you can put a CFT on a manifold which doesn't have enough isometries to get into the conformal group. But yes, anyhow, for the sake of today, let's not get confused. I'll just think of straight defect essentially most of all the time. Sometimes circular defects in Euclidean for formal reasons.
But the reason I'm asking, because usually in CFTs, when we talk about local operators, there is state operator correspondence, right? So really we can talk about state, but we can talk about operators. And for defects, because naively also, if you map it in a small circle, then you may think also it can be some kind of state operator correspondence.
So there is a state operator correspondence, but it's not useful to think. So what happens in CFT is that operators placed at the origin, and then you quantize in radial quantization, corresponds to states, right?
Yes.
So here you have your line, and operators placed at the origin of the line, again, which correspond. Defect operators here.
No, but I'm thinking about different. That's why I asked my question. If I now map this, because I can conformally map a straight line into a small circle, right? And then it looks like I may think about.
You can decompose the defect into a sum of local operators in the center. That's what you're asking.
I'm considering the defect which is a circle.
Yes.
Not a line.
Yes.
And then I may think of that defect creates a state at the
center. Yeah, that's correct. That's a correct picture. So, okay, it's a bit informal what you were saying, but if you have a defect in a straight line,
right,
you can expand it as a sum of local operators at the center.
Right.
With some kinematic factors. So that's correct. So essentially it's like a multiple expansion. If you like if you have a non-local object, but you look at it far away, you can always think of it in terms of something.
From that point of view, it doesn't look like there is a big difference between defects and local operators. So defect.
But it's an infinite number. It's an infinite sum here. So that's why.
Right. But in terms of, is it in this language, is it possible? Because I different infinite sums, and not all of them would correspond to defects. Right. So characterize in this language what infinite sums are kind of interesting.
For example, will have symmetry. So one criterion is that it's going to have this as L2R times SO2 minus 1.
I mean, I think this coefficient here, if this defect is conformal, constrained by conformal symmetry as well, there are some kinematic factors which are essentially one-point function operators in the place of the defects. So if this wasn't conformal, like here you could have this, here you could have arbitrary powers. Here instead you would have essentially x to the delta O essentially.
Which is related probably to what.
So it's essentially what Tiffany was saying. So this coefficient here are fixed by conformal. Okay, so let me get quickly. So once you have a defect CFT, we can characterize it pretty much as we do for CFT. So we have defect operator spectrum, leading on it, which will be classified by the representation that's R1. So it's scaling dimension again. So if you think of this number, you can think of this number as extra critical exponents associated with the defects, and this is typically measurable in condensed matter experiment, for example, for the impurity. You also have, even though I won't really need it, about the defect of E, which was something related to what Sergei was saying, that you can expand the bulk operator into a sum of local operators on the defect. And this is essentially useful if you look at correlation function bulk operators close to the defect. A comment that might not be obvious is that the defect operator spectrum and the bulk operator spectrum, they are typically totally different things. For instance, the defect again may also have quantum mechanics that doesn't live in the bulk. And again, the formal way to trigger an RG flow is to add a relevant perturbation to the defect. And this is not such a theoretical construction, so motivate. So an operator is financial as one. So a conceptual point that I want to make is that the defect RG flow also has its own monotonicity theorem. So the starting point and the final point of the defect RG cannot be the same. Okay, this was something that has been known for a long while in 2D, and it has been more recently proven this joint work with Zoe and Adia for in higher dimension. And the result is, I want to explain, is that if you consider the partition function for a defect placed on a circle, minus the partition function of the theory without it, the result is called log G, and this is decreased monotonically under RG. So this inequality, essentially, there is a characteristic of the defect that in the UV fixed point and the R fixed point must be monotonically decreasing. So this guarantees that the two theories must be different. Comment is that a theory without any defect has G equal 1, just because these two cancels out. So log G is equal to 0. And G must be bigger than 0 in any unitary theory. Okay, so I'll use this result. But notice, I mean, from the experimental viewpoint, placing a defect on a circle is not something very natural. So this is really more useful on a theoretical level. Okay, This discussion was a bit abstract, so let's try to get more concrete. So there are three natural ways to construct defects, and each of them has its own experimental applications. Well, there are many natural ways, but there are three at least that are very, I think, simple from this perspective. The first one is start with some bulk CFT. Could be your free theory, could be not, could be something more exotic, and you add and you integrate along the line an operator with scaling dimension less than 1. This is a relevant perturbation, so it must lead to some RG flow. You can also take a bulk theory, couple it to quantum mechanics, and then add the relevant perturbation that couples the quantum mechanics and the bulk theory. And the most complicated example is the one that we will study the most in textbook. You take the bulk theory, couple it to quantum mechanics, and you gauge the group of the quantum mechanics. So the quantum mechanics is some n-dimensional representation of the group G, and you gauge it. So this is typically gauging the color degrees of freedom on the line for a Wilson line. Okay. So let's get what this means in practice. So I'll start from the simplest one. Okay, let's finally get to a concrete problem. So concrete problem, I'll take one model. One model, if you want, is a model for the magnet at the critical transition point. So in the critical point. So it says schematically given by this action. Schematically because the theory is really strongly coupled to the equal phase. And now I'll consider what I said at the beginning, the effect of adding a magnetic field perturbation. So the magnetic field, how do you model it in terms of the continuous description of the quantum field theory? Well, it's an integral in some parameter tau, known in Euclidean, at some location which I take to be x transverse to 0, of h, the strength of the magnetic field, times the order parameter pointing in one direction. So this symmetry breaking breaks ON, this term breaks ON to n minus 1 because the magnetic field is picking one direction in the UN space of the field.
But when you have this picture with individual units, you're still discussing continuous theory, right? So it's not a lattice.
This is what describes this. I mean, in the long range limit, this lattice is described by the ON conformal field theory. So that's
but when it's a continuous limit, then I would think that magnetic field would be not on one particular side.
It can be on a bunch as long as it's sufficiently localized. I agree.
Yeah. So in this way, those circles are not localized.
So yeah, I mean, if you want, after you perform RG, this doesn't need to be a single atom point or a single lattice point. Yeah. This can be around a few lattice points as well, of course.
Yeah.
That's totally true. Yeah, it's like, for simplicity of thought, I think of it like this, but you're totally right. Okay, so where does the machinery we said before become useful? So now, the scaling dimension of delta pi in the bulk is known, close to the equal 4 is known from free theory, and in general is known from non-perturbative result, bootstrap, Monte Carlo. So it's less than 1. This is a relevant perturbation according to the classification before, so it must lead to a defect RG flow, so it must lead to something non-trivial in the interval. Now we said this setup has been studying in Monte Carlo and also in some experiments. And when we say Monte Carlo, this is particularly useful because it allows to tell you, when you approach the transition point from the ordered phase, this magnetic field tells you where your lattice will align in the ordered phase. So it allows to augment precision in the measurement of the critical exponent. So there is some application of this thing, it's called the pinning field. But okay, let's make it. So what can we do? As I said, this problem is strongly coupled, so we can study in regimes where the model becomes quickly coupled. So we can study close to the equal 4, where you have the epsilon expansion. We can study at large n, and close to the equal 2, because you can have exact solutions there. Okay, so close to the equal 4 is standard perturbation theory. There's nothing weird, it's perturbation theory in the quartic coupling, so it's something we know to do from standard 15. Large n is more complicated. You have to find a self-consistent solution. It turns out that the coupling of the defect scales with n, that's per root of n. So this means that you need to account for it consistently in your description. So it means that this will shift some of the saddle point of the large n discussion. And surprisingly, I'll probably say quickly that results in the DS loop diagrams were really important to solve the theory there, because essentially the conformal one-dimensional conformal group is the same isometric group of ADS2, so you can translate some results from there to here, but it's a really technical point. In 2D, you have exact solutions for n equal 1 and n equal 2. You can do 2 plus epsilon expansion that you might have heard for n larger than 2. And what will be the trick to get predictions is that you solve in 4D, you solve in 2D, and okay, you get several orders, and then you try to extrapolate to the equal free. This will allow you to get some leverage in the predictions. But yeah, so essentially it's the only way we can get prediction equal free is trying to play in this game. And we're not guaranteed it will work for the observers. Okay. So how do we do that? Let me start saying, so let me start from the 1 minus epsilon expansion. So this is a sketch of a calculation you might want to do. You might want to compute the 1-point function of the order parameter. So we want to compute the order parameter at some finite distance from the defect to equal x. So at leading order in the perturbation 2 in the bulk coupling, you have only one diagram that connects the scalar field to the defect, which I denote with this black dashed line. So nothing fancy, it's just one propagator, you have to integrate over it. Totally do it. Next leading order, you can attach it to port coupling, to portic coupling, so you'll have diagrams like this. And then so forth so on. You will always be able to attach more and more to the defect. Notice I take into account arbitrary insertion of the H coupling at the defect, but I am perturbative in the bulk port. So I'm thinking now the magnetic field really as an extra coupling. Okay, here you do diagrams, you compute them, you find divergences, and the only way to absorb the divergence is to shift your coupling gauge as if it was to mu complete constant, and therefore after you do that you can compute the beta function. So this is the result if I for the beta function. This is what counts by being in 4 minus epsilon dimension, and this is what counts from this one loop diagram. As usual in the epsilon expansion, you equate them, you assume that the portic coupling is also tuned to the portic critical point, you find that a 0 at this value here. So H scales like square root of n as promised. And you can think of this picture as an energy flow from the situation where you didn't have any magnetic field to the one where the magnetic field becomes some critical value. So the flow stop. This is a very concrete realization of the defect of the three-dimensional being. Okay. Questions here? Okay. So let me give some details of how you do large N. Not too many. So how do you study the UN model at large N? The UN model at large N, you typically...
Gabriel, sorry, I have a very dumb question. Can you go back to the formula at the end? So you take epsilon to 0 in the end. This is in d equals 3 plus 1, right?
So this is in 4 minus epsilon. So
4 minus epsilon, right?
Yes, so I take...
So you take epsilon to 0 there, but you say it's...
I don't take it 0. I take it small.
Small, okay.
So, yeah, maybe...
Ideally, you take it to 1.
So, actually, ideally, you want to take it... So, you want to solve your 3 and d equal 3.
Okay.
But the only way we have to do is essentially be 4 minus epsilon, or 2 plus epsilon, or n to infinity. And then we have perturbation theory in epsilon, or you want to...
You say when it gets strongly coupled, like lambda...
So, lambda is of order epsilon. So, if you want, once you take epsilon to 1, lambda becomes order 1, and you can don't have perturbation theory. So, yeah, I mean, somehow if you, for the bulk critical expansion seems to work fairly well. So, that's one reason to try to do that. And somehow it worked out for us well.
Gabriel, so have people tried to study, actually just in the 3 dimension, this particular line by using bootstrap? I mean,
Monte Carlo. We did in Monte Carlo for the icing. And I was going to show in a moment that our predictions obtained this trick of extrapolating actually match the Monte Carlo.
But there's no bootstrap study of this line.
As far as I think people are thinking about it, but no published study yet. So I don't know if it's not clear how easy it is to from the bootstrap. Maybe we should discuss. Yeah, so it would be nice to have a non-perturbative understanding. Okay, so yeah, how am I doing time? Yeah, I feel okay. Maybe this is potentially large N solution, but maybe this is a bit extra technical. So maybe in the interest of time, and maybe also in the interest of questions at the end, let's keep that. I think. So let me just say that you can study this problem in the large N, and you find results also in the n to infinity limit. Of course, you would really want physical materials have n equal 3 or free model. It's like this. So of course, I say why am I doing it to infinity? That's because the best I can do. But essentially, you find some results. So there is first of all an exact result which is there is an operator with scale dimension 1 for any value of n larger or bigger than 10. This counts, operator is protected by symmetry. So why is that? So when I told you that I pointed the magnetic field in the one direction, it was my choice. I could have pointed in the direction 2, 3, I could have rotated it. So from the viewpoint of the action, means there must be a margin of deformation that accounts for this rotation. So I'm allowed to modify the direction of the magnetic field without really changing anything in my theory, because that's a choice. So there must be a marginal operator to account for that, and this is called the tilt operator. And it must exist for any n bigger than or equal to 2, like I rotate the magnetic field. So it's just for model entities. We also computed some scale dimension which is less trivial, which is the lowest. So the lowest dimension critical exponent is 1.5. You can associate it with the operator phi1. It essentially tells you the correction to criticality in this defect. We obtained this prediction extrapolating it in 2 plus epsilon for minus epsilon and m from large n, and it turns out that it's actually independent of n up to the second digit. So that's why I'm not sure dependence on n. And we were very happy because this prediction is actually consistent with Monte Carlo results for n equal 1 and with the infinity results. So it seems like somehow with this trick we got lucky. And of course, n equal 2 and equal 3 there is no non-perturbative study, but now we are confident for that. We also obtained other quantities, 1-point function, partition function, but we weren't able to extrapolate them exactly. Nonetheless, you can compute them. Let me just say one thing, is that the log of g, I told you, should decrease under the Rg. Log of g starts at 0 here because of the trivial defect. So you can compute the epsilon expansion, so for epsilon small, and for n very large, in equal 3, and you find it is negative. So the theorem I mentioned before is satisfied. But okay. Okay. So why are these results useful? Okay, you might say, who cares, it's something people did only in Monte Carlo. But now I'll show you these are connected to stuff that you can actually do in a lab. Again, I'll take again my favorite lattice picture, and I'll think again of the OM model, in this case particularly of the O3 model. So phi is really a triplet now. And I'll consider the case in which the bulk is critical again. You can even consider the case where the theory is free, but I won't do it in this seminar. And now, if you were to model in the lattice this system, how would you model? You add an impurity, and what would you do? You would add a localized term in the Hamiltonian coupling the bulk or the parameter to the spin of the impurity linearly. That's the way what you would do in your lattice. So how do we model this in field theory? So I'll focus. The way to model this in field theory is to borrow from what we know of Wilson lines. So your defect now is written as a trace of a path order exponential of phi times a metric state. Why is that? So the trace is over 2s plus 1 states, which just represents the 2s plus 1 dimensional Hilbert space of the impurity on the spin, of the spin impurity. So this has some spin, it has some phi dimensional Hilbert space. Path order
Come on, imaginary?
no, you don't need
T is Hermitian?
T emission. And gamma is not imaginary. I mean Euclidean time now. Sorry, I should say that.
But you still want it to be unitary, right?
Yeah. If you are in Minkowski, this would be, yeah, you're right. In Euclidean, this is real. In Minkowski, would be 9. So phi dot t is just the most natural way to write this coupling. So t is a representation of the SU2 group with the appropriate dimension. So that's what you can do. This is precisely this coupling here. And now I have to allow for an arbitrary number up front because I am ignorant about my microscopic model. But this coupling idea will flow, and I want to understand the endpoint of the flow of this coupling. And I will, as you see in a moment, it's quite independent of the two quality coupling. Again, I'll focus only in the bulk interacting case, which is the one that's actually relevant. So, okay, again, we will do what people can do. Again, the O3 model is strongly coupled in equal 3. The model of the impurity is also hard. So again, you look for approximation scheme. People did it in action, a very nice science paper of Sachdeva and others 20 years ago. And what they did, they looked again at the theory close to the equal 4. So they took a finite epsilon, 4 minus epsilon, and they computed a beta function for this coupling gamma. This comes, it's non-trivial, okay, so just diagrammatic calculation, I do more detail. But this is more or less how the result looks like. It does a term in gamma cube, a term with the vortic coupling in gamma cube and square, and so forth. So if you want, this is one loop, and this is two loop result. Now you can look for a zero of the beta function again as I did before to find for the fixed point. The result is just this. So gamma is for the epsilon, and then you have an epsilon squared s squared correction. So then people tried to extrapolate the formal reception expansion result to the equal free, and the results were not consistent with quantum Monte Carlo, for instance. There was no reason why they should be, but that's what, for instance, in our case it was, so people tried. But what I want to observe in this formula, which will motivate a way to do better, is that this term here, which is actually subleading because I'm taking small epsilon, this is epsilon squared, is actually not subleading when S is sufficiently large. So even if I want to study it in 3.99 dimension, if I take S sufficiently large, such that 0.01 times S squared is a further 1, this term dominates and perturbation theory breaks down. So it means that for impurities with arbitrary spin, even the epsilon expansion fails. So this motivates us to look for something better, which hopefully might extrapolate better also to the physical case. Again, I'll just, okay, here, this is supposed to be green, sorry guys. So just a quick summary of what we did. So you can summarize the situation as follows. The blue region is the one where people could do perturbation theory before. So it's small epsilon, but as you increase S, epsilon gets smaller and smaller. It's like epsilon squared fixed here. So people could study the epsilon expansion all as long as S was sufficiently small. We devised a way, which I won't explain, to do perturbation theory as long as epsilon is small and for arbitrary S. So we resounded our just effects of the perturbation theory. I won't show that, but instead I want to highlight this green region here. This green region here is essentially an effective field theory description that we propose that should hold for arbitrary D as long as S is sufficiently large, or better, as long as epsilon S is sufficiently large. So the reason why this is nice is because it applies also in 3D. So if you were to put a doping atom with spin 10, your system expects this description to give you the predictions. And this description is nothing but saying that the large spin of the impurity acts essentially as an external magnetic field defect. So the result I showed before will translate here just by copy paste.
Which is the reason for which it fails when epsilon becomes very small, so you're close to the D equals 4?
So the effective field theory is an expansion 1 over epsilon S squared essentially. So if you're in the equal free, it's really 1 over S squared. If you're like close to the equal 4, it's just 1. But one thing, okay, this is not apparent now, but one thing I want to say is that there is an overlap between the full perturbative regime and the effective field theory. And in this overlap, you can check perturbative this proposal works.
The question, so the blue and the green don't overlap?
Right.
No, because the blue is, yeah, so the blue is the parametrically opposite regime. The blue always solves a small s, so you cannot solve it to large s. Okay, so this is the main result is that effective field theory is an angle average of external field defect. So you take a magnetic field defect and then you average over the angle, the prediction, just because the spin of the impurity has no reason to point in this direction or that direction. So you have to average over the in the end, plus some decoupled degrees of freedom on the line. So the results therefore follow. Before I showed you that it was a scaling dimension 1. So here this will be a vector scaling dimension approximate 1 up to 1 over S correction. There was an operator dimension 1.5 in external field defect. Here the same up to 1 over S correction. And we can compute some of this 1 over S correction, for instance, for the spin of the impurity. Let me also say we try to extrapolate some of this prediction to S equal 1/2, which is where there is quantum Monte Carlo. Of course, it's a big stand. There is no reason why it should work, but it seems at least to do as well as the previous one, if not slightly better. So there is reason to believe it's a good way to proceed. Okay, so let me finally go to something that's more familiar, which is Wilson lines. Wilson lines, from the formal perspective, is about CFT, quantum mechanics, engaging the group of the quantum mechanics. Last class. Okay, so I think you're all familiar with this formula. You take a conformal gauge theory, not conformal at this stage, and you write trace in a representation of the gauge group of the factorial exponential of the gauge field contracted with T. And the question I want to ask is, what is the space of Wilson lines in the interacting gauge theory? This is an hard question, even though it doesn't seem so. For instance, it's known from lattice of QCDs of Young-Mills theory that even if you put a Wilson line in some arbitrary representation R, actually QCD or Young-Mills will want to create gluons that will get attached to the line. And this gluon will screen the charge of the line to the maximal possible extent. So if you put a actual line in the adjoint, in the lattice of sufficient for distance, you don't see anything. I don't think there is any non-perturbative proof, but it's evidence from numerics. So, for instance, again, the end upshot is that the number of independent lines in that case is not labeled by the representation R, as you might have guessed, naively, but by something which is called the analytic. So there is essentially only, in the case of SU2, for instance, Young-Mills, it's only the fundamental line. Okay, so if some of you is bothered that this question is not pretty well defined at this stage, but it's something that bothers us is that we didn't know how to well define this question in general. But at least in the case of CFT or quasi-conformal theories, there is a very mathematical way to phrase the question, what is the space of Wilson lines? Which is, which Wilson lines define a non-trivial defect conformal field theory given in a definite conformal gauge theory. So in other words, if I write in a perturbation theory something like this, is this defining a unitary defect conformal field theory? So naively the answer is yes, because this line doesn't have any coupling here up front. So the size of this is fixed essentially, so this number here is fixed by gauge invariance. So there is no random coupling. Naively, you think there is all representation are defined a Wilson line. In other words, if you think of the nucleus, every charge Q of the nucleus is allowed. But as I said at the beginning, you have a large electric field. In another brilliant case, the Coulomb potential will be something like the highest weight of the representation over R times G squared Young-Mills. And therefore you expect an instability due to the Schwinger effect. So let me study this question in the simplest possible example you're all familiar with. So I'll take a Wilson line, take scalar QD. Okay, so this is the action scalar QD that you know, and I tune the mass to 0. If you want to think of this in a physical setup, you can think of some superconductor close to the first order transition point. But okay, well, just take this model. I'll work in a classical approximation, so I won't have to bother about beta functions. So the theory, couplings are small, the theory will be quasi-conformal. Here is my Wilson line that I added to the action. So it's a charge Q object, so it's just a model of a nucleus. If you want to make more precise, I'll do only classical physics, but if you want to make this more precise, you can think us working the limit in which the coupling goes to 0 together, is square like lambda, the charge goes to infinity, and this product is fixed. But you don't have to if you just trust me. Okay, so the question on whether a Wilson line defines now a good defect conformal field theory is just a question whether expanding around the saddle point sourced by the line, which is just a Coulomb potential, a trivial scalar field, there are instabilities in my theory. So do I have Growy modes for the scalar? So in other words, if I write the equation of motion for the fluctuations of the scalar, I may even find solution with positive frequency or with imaginary frequency. If I find imaginary frequency, it means that the scalar wants to grow and there is an instability. Okay, I won't do that analysis by writing a hard equation and solving them.
Sorry, very stupid question. Doesn't it depend on the sign of the positive of the imaginary part of the frequency, like if it is growing or what?
For scalar, I think you can show that it must always be growing. So for fermions, I think you're not going to have a scalar solution. But yeah, of course you're right. But so I'll rather use a trick, at least for those of you who are familiar with the CFT would be convenient. If you are not familiar, you just trust me, this is a way to get the result. So I can rescale my metric from flat space to a manifold which is called radius 2 times the sphere. So what you do, you write your metric in cylindrical coordinates. I don't know why I have it in Euclidean, it should be in Lorentzian, I apologize. This is the sphere, r squared, lambda squared, you multiply and divide by r squared. This is radius 2, this is the sphere. So now, looking for stability of the scalar is equivalent to looking for which range of masses in radius 2 I am allowed to look at. So in other words, I have to do a Kaluza time decomposition of the scalar of the sphere, and then look at the radius 2 mass, which is something like the angular momentum, minus the contribution of the gauge potential, which because of this metric here is now constant and looks like this. In other words, what I'm saying is that the fact that there is instability is reflecting the fact that in this equivalent description, the mass is negative. Okay. So anyhow, the upshot of the analysis of this perturbation is that they have to look at the solution of this equation here. So I look m naught squared, so which is disappointed here at time equals 0. So I'm looking at the homogeneous mode. And
Sorry.
if I
It's just negative because it's the high dimensional layers, you may have tachyonic mass if it's not tachyonic, right? So,
I didn't say how negative it should be for instability. Of course, I have to compare with the BF bound.
okay.
So anyhow, so if you don't know what the BF bound is, I'm just saying you have to take m naught the mass in ADS and equate it to delta naught minus 1, where delta naught turns out to be the scaling dimension of the lowest operator on the defect conformal field theory. If this equation has real solution, then I don't have instability. If it has no real solution, I have an instability. That's the rest of it. So this equation has real solution as long as m squared, it can be negative, but not arbitrarily negative. In particular, as long as m squared is larger than the BF bound, as Sergei recalled, which in terms of E and Q, and I'm taking Q positive, translates that E squared Q should be smaller than 2 pi. In this regime, I have two solutions. Delta naught and 1/2 plus square root and 1/2 minus the square root. So this solution here is just the Wilson line that you all know, which has an operator scale dimension 1 starting, but it has some anomalous dimension correction coming from the potential. But the second solution corresponds to a different boundary condition for the scalar. So in other words, I'm saying that to specify Wilson line, I have to tell you also a boundary condition for the scalar on the nucleus. And this solution corresponds to a different boundary condition, which is related by RG, as I'll show in a moment, to the odd one. So I have two conformal boundary conditions for the scalar given a Wilson line. And to answer the question about the stability, once I get T squared Q sufficiently large, there is no real solution. Therefore, this means that the theory is unstable to the presence of growing mode, and if you are equivalent to defect conformal field theory is non-unitary. So if you put a nucleus with charge that exceeds 2 pi, you get an instability. Maybe it's worth commenting that something like this happens also for fermions, even though I won't discuss it really. And in this case, the bound is Q squared over 4 pi, which you, as you know, you can write, if you write Z, in nuclear physics Q is Z, alpha is bigger than 1, which tells you that the charge of the nucleus should be less than 137. This is a result actually of Pomeranchuk of 45. He was studying the Dirac equation in a Coulomb potential and found that the Dirac equation doesn't admits an instability, so there are not anymore states when Z exceeds this value in real life. This is not, and it's actually no, if you think of physical nuclei, there are no nuclei with 137, so there is no contradiction in nature, of course. In fact, due to the strong force, nuclei start existing on 110. But there are situations where you can probe this stability experimentally, actually, but I don't think I'll get to that.
So coming back to before, so is there, because that's very Lorentzian description.
Yes.
If in Euclidean signature, instead, as you said before, if Q is real, that it looks like it's always bad because it's imaginary.
Yes.
And if Q is imaginary, is there any problem?
If you put an imaginary Q in Euclidean, we haven't thought about putting an imaginary Q in Euclidean. I don't know, what does it mean putting an imaginary Q? Is it an engaging variant putting an imaginary Q in Euclidean because you want that on a loop, a large gate transformation is, you want that the large gate transformation just results in a phase once you put the Wilson line on a loop.
But
So
that's a
don't
normal Wilson line, because isn't like when we discussed.
No, the normal Wilson line is to the IQ also if you rotate also the gauge field. So the normal Wilson line suffers of the same problem.
No, because when you are in Euclidean signature, right, like lattice people do, they always study Wilson lines, and they are perfectly, there is no,
They find screening. A Wilson line. So I mean, I'm not saying that it doesn't exist a Wilson line. I'm saying there is no conformal line. So you must define it with a cutoff, and then you must ask what happens once you put the cutoff, and I will show that there is screening. So there is, I think what we find is kind of consistent with what we find.
So the interpretation of this is that there is no conformal.
There is no conformal line,
Okay.
so there is no UV complete description. But you can still, you can still imagine, if alpha was not 137 was 1. So this happens actually in graphene. Alpha is order 1 for a layer of graphene. You can put a nucleus of charge 5, you violate this instability, but the nucleus, and there is no problem because the nucleus has a finite size, has a some cutoff, so you don't need to have the complete description. But as a result of the instability, matter will accumulate towards the nucleus and will spring the charge.
But again, in the Euclidean picture, because you're saying, oh, the bad thing about it is that it's complex. But that becomes complex at any value of Q. So how to see in an Euclidean language that there is this critical value of Q? When
I
it's
think
complex?
it's literally the same. I'm solving, I'm solving the mass of the ds equal delta minus d. I mean, this is the thing which we always do, and they not will always. I mean, the physical electric field is imaginary. In a Wilson line source is an imaginary electric field in Euclidean solution.
Okay.
So that's how you see that the sign source stay the same. I don't think there is any difference.
But you're saying there is some critical imaginary electric field which is bad.
Yes. Yes.
I mean, not just the fact that it's imaginary.
If there is a critical one, yeah. I mean, we can recreate electromagnetism and get an imaginary electric field. That's something we know, but I'm saying here, if you do, here, well, you cannot for certain values of Q. So the problem is varying valences, which is important.
We are looking for a UV fixed point. This is in 4 dimensions.
Yes.
But the scalar electrodynamics is not UV complete.
I'm neglecting one loop effect of the beta function. I mean, the mathematical way to phrase it is that I'm working in this double scaling limit. And in double scaling limit, one loop effects are suppressed. But I mean, I could have done the same in an equal 4 super young means if you wanted to be pedestrian. There is a, okay, you might not see how to write this term in equal 4, but there is a way. And but okay, I thought it was simple to discuss this example. But many of these claims apply also in theory that we know they are conformal, And
But sorry, so are you planning to make a statement about the similar kind of instability for superamulets, or?
it's the same statement. You just replace E square with G square young means. That's the same statement. Well, I mean, okay, say n equal 2 with 4, no, n equal 4, yeah. Just
But only for the non-supersymmetrical of that.
Non-supersymmetric Wilson line. I'm not talking supersymmetric Wilson line, but supersymmetry is guaranteed to be
Yes.
degenerate with the ground state, so they cannot have any stability.
Yes.
So I'm only talking about non-supersymmetric.
Good. Good.
Okay.
So even though in the Euclidean signature this will be imaginary electric field.
Yeah, we can discuss it later. I think, yeah. Okay, so I just wanted to give you a picture of how this happens. So I told you there are 2 conformal boundary conditions, so 2 for the nucleus, and these 2 are related by RG. So something known from a CFT is that a double trace deformation leads you to one boundary condition to the other. So this means that on the line there is a natural coupling, G, which has this beta function here. And here I plot the beta function. This beta function has 2 fixed points when you are subcritical. Just 1 when you are exactly critical, and 0 when you are supercritical. This gives you a situation of Minkowski scaling. And the flow happens like this. So why is this interesting? Again, if you imagine the CVS setup of a nucleus, there is no reason why you should be either at this fixed point or this fixed point. It will just be generic at some point of the flow. So if you're in a situation where you are sufficiently close to marginality, to this point here, this flow will be very long. So if you measure observables, you will see some logarithmic running or quasi-logarithmic running, say in the phase shift and stuff you see. So I'm not detailing that, but I'm just saying this flow can be very, very long, and therefore it can lead to stuff you can predict. Okay, so maybe let me just answer what happens if I put the supercritical line. So supercritical line doesn't define a UV complete theory, but I can still put it with a cutoff. So this is the radius of your nucleus. You saw it's a problem electrostatic. You will define some electric field on the ball here, and then you have to tell me some boundary condition for the scalar field. And the most natural thing is to assume that it's 0 on the ball, but the result doesn't really depend too much on this. And then I ask, what is the minimal energy configuration? So what is the ground state? It's again a classical physics problem, it's approximation. And that's what you find. You have to do it on a computer, but you can understand some pictures and a bit. So this is so here I plot the scalar field times r, and here I plot the electric field times r squared. Sorry, this should be log r over r naught. Should be a logarithmic plot. Oh no, it's r over r naught, guys. It's logarithmic scale. So r naught is the cutoff. So the electric field starts at the value that you set, of course, but then the scalar field grows and the electric field passively decays. So this means that as we anticipated, the matter accumulates again around the line and squints. The electric field instead decays also, but all very slowly, logarithmically. So this means in formal terms that there is a flow from this non-conformal line to a trivial line, so to the theory without any line. Because both of these decays faster than their natural power, which are r and r squared. One nice thing is that the size of this cloud that you form is actually exponentially large. This follows by solving the beta function. So the beta function has, you have a beta function, so you have some dimensional transportation, actually something non-conformal. And once you are very close to the criticality, the size actually of the cloud is something like x 2 pi over that square root. Something like this. So if these square roots which are close to the marginal line, then this becomes very small and the size of the cloud is very large. So if you can set it up somehow, you can observe. And let me say that there is also a similar flow. Before I told you there is a flow between the two boundary conditions on the nucleus, but there is also a flow from the new or UV boundary conditions to the trivial line just by adding the perturbation I showed before with the negative sign. So in principle, it might happen. Means I don't know in which situation in practice.
Sure. So for this, for the flow from the non-conformal line to the trivial line, how does the G function look like?
From the non-conformal. I mean, there is no G function here.
So the G function, but in the intermediate stage, it is like you gave me this kind of local description of the line, and so you can compute the G function. Is it monotonic?
I mean, we didn't check with the defect entropy.
I'm just wondering, like, for this kind of non-local object, whether the G function still makes sense to some extent.
No, I think you can make sense of it. We just didn't check it. I think I agree.
So you can still define the free energy, right?
Yeah, we can define partition function.
Right.
I would need to think to be. I mean, here we can compute it. Here
Yes.
maybe it's harder to think of a stuff numeric. But yeah, the GTN should see all. I mean, we just didn't check it. Okay. So let me just say that this is just the beginning of our rich story. The question about what are the space of Wilson lines in gauge theory, conformal gauge theory is application to superconductors, as I said. We can do fermionic QD. Big difference here is that there will be only partial screening due to the fermions. So fermions will always screen exactly to what's very close to criticality. So if the bonds are equal to 37, we screen to 136. Just essentially because you feel levels rather than creating a Bose-Einstein constant cloud. There is application, formal application for these CFTs, chemical force by emitters. And then you can do 3D theories with 4D gauge fields. And this is nice because you can do graphene, and some of these things were explored, but many not. And then you can do also 3D theories which are purely three-dimensional, like large enough QD or Chern-Simons, and also there are some stories. In other words, I mean, there are tons of applications of this. So stay tuned for this. Okay, so I'm gonna close now. So let me just summarize. I studied some line defects, applications. In particular, I studied magnetic field defects, large spin impurity, and Wilson lines. And there are some questions. Some are more theoretical. So, for instance, some of them have been there for a while. So, we mentioned this G theorem. We may miss an entropic interpretation of the G theorem. I mentioned the question, and there are some more critical questions about lower bounds on the defect partition function, which would be kind of a lower bound on the G. And there is some nice work in 2D, including the work of Ifan. More concretely, my task, can we make more prediction for the models I studied, in particular for the impurity? It would be very nice to have a bootstrap approach, but it's not clear how easy it is. So like non-perturb, but it's really not extrapolations. And then, I mean, we are now revisiting Wilson lines in weakly coupled gauge theories, but it would be nice to revisit them from the holographic viewpoint. So with that, I think I'm not thank you.
Thank you.
Sorry, I am a bit confused. This results for the Wilson line, at least in the large charge limit, do not depend on what the theory in the bulk does. I mean, it could be the your results do not seem to depend on what is the RG flow of the bulk theory, right? Because it will go to a strongly coupled.
So I'm assuming that there is no RG flow in the bulk. So in this approximation, neglecting the beta function of QD. So if you want the double of the QD beta function, and is scales which are much.
And so, what would happen if E square is small but not non-zero? Say, because then you have a difference whether you have, say, a mixed theory that's confining, one that's conformal.
For confining theories, I cannot say anything. I wouldn't even know how to face the question. So I need that the theory is nearly conformal. So yeah, so I mean, let me say that the instability comes by looking at the R equal not from the where the electric field is strong, so for small r. So this instability will be there in also for massive theories as long as you're allowed to go very close to the line. But you know, what is the fate of the instability at long distances really depends on whether it is massive, on the G flow. So that's why if you assume a conformal gauge theory, I think the results will be similar to the one we showed. Otherwise, yeah, it's more low.
Yeah, you mentioned a few times that some of these phenomena are measurable in real condensed matter systems. So which one do you think is easiest to test or has already been tested?
So okay, some things have been kind of done. So like three-dimensional theories with gauge fields have been studied by Gabriel, but there's some nice work by Levitov and collaborators, 2007, where they essentially noticed the same instability and they studied that screening, and that has already been observed, but it's not our work. I don't think they noticed that these are G flow reduced to boundary conditions. I don't think they don't. What we find is there should be some logarithmic correction to phase shift that are measurable.
So what do they do precisely? They put some large.
So they put some nucleus with some charge which is sufficiently large. Arc is order 1 for graphene and batteries, so already 5 is good enough. And they observe that the Fermi serial ranges, so to screen, so they feel some levels before what pulses around. And they may have a description of that. What we believe should be observable is like if you probe with some neutron scattering experiment, you measure the phase shift of the states. Even in the stable case, there should be some logarithmic correction because there is a running, this energy running of some parameter. You can just think that this picture just means that there is some log, of k times the size of the cutoff and the phase shift that you should be able to measure. And I don't think this was done, and I think this would be a promising direction to see something. And yeah, we are thinking also whether really the story I told you, I mean, this is a model for superconductivity in 3D, so close to the transition point. We're thinking whether really there we can say something new, measurable or not. And it's important, as Massimo asked, to see that how important are deviation from conformality in that case. But that's still.
So you mentioned this connection to holography. So I guess a natural question is, what is the interpretation of this instability for the large charge Wilson loops on the Holographic side? So in that case, I guess the dual description will be some geometries. For example, you're considering for Mills, the large charge Wilson loops, depending on how large the charge is, can be described by multiple deep rings or actually some new geometry. So do you expect this instability to be tied to instability of the geometry?
I don't. So I don't know. I mean, I know that people constructed these Dublin geometries, for years for superconformal lines that strongly react.
Yes.
But you need to go away from the superconformal limit. So I don't know how to do that. And so would that be an instability geometry? Yeah, I honestly really don't know. I think it's a good question. I really think that I don't even have a good guess for what the geometry would be. Also, I mean, notice that somehow this is so is it yeah, so this thing here does the coupling, so you have to understand how this is extrapolate a strong tooth coupling.
Yes.
So Okay, namely, my series is the tooth coupling divided by n, so maybe you want to take charges of order n. But even that is just an extrapolation of this formula. You might not do that.
And so what happens for magnetic?
Tooth line.
Tooth line, yes.
Okay, we don't know, but I mean, if you take this formula in an equal force over units, then you have a SL2Z duality, and then it seems to say that there might actually not be any tooth lines just because we invert the coupling. So, in a weakly coupled and equal force over units, maybe there are a bunch of Wilson lines and not tooth lines. Okay, just extrapolation of this problem. I mean,
But isn't it a little surprising because the supersymmetric tooth lines can be thought of as a deformation of the non-supersymmetric ones? You're saying that even though the supersymmetric one exists, I can turn on a deformation and remove all the scalar coupling supposedly.
I mean, you see, it's not that there is no line. It's just the solutions are there are some deltas that satisfy this equation, but they are complex.
Right, and they flow to trivial. Right, that's the.
I mean, if you insist that this is a unitary theory, yes, but if you put complex deltas, you can have some non-unitary CFT defining the line. So maybe it's a deformation of that. What you're doing is still mathematically allowed, I would say. It's not really defined. But yeah, I mean, as I said, I mean, all I'm saying is I'm extrapolating this formula here to the using duality, using the SL2Z. So maybe there is some subtlety using that. We didn't do any calculation there for 2 lines, which is hard to say this.
So in your analysis, even in a conformal theory, you need E going to 0 and Q to infinity.
Yeah, I need the charges which are order 1 over this units. So I need size of the highest weight of the representation. One charge should be order 1 over this units.
All right. So let's thank Gabriel again. Recording.